So we are very happy to have Liz from UC, Berkeley, and she will tell us about the black hole cannibalism.
Hello, thank you very much for the opportunity to speak today. I'd like to share with you some work I've been doing with Ning Bao for the Gravity Research Foundation Essays on Gravitation. And we've entitled our work Black Hole Cannibalism for reasons which will become evident momentarily. But very broadly, I'll be presenting a thought experiment, discussing some interesting, potentially problematic implications from this thought experiment and some potential resolutions for this. So first, I'd like to start with a framing question, which is one with which I'm sure many of you are familiar. And it's the question of whether, if someone throws a message or quantum system into a black hole, is it possible to reconstruct or recover that message from the Hawking radiation? And by reconstruct or recover the message, I mean that you can do anything that you could have done with the original system, with this reconstructed system. And again, as I'm sure many of you know, Hayden and Preskill in 2007 discussed and demonstrated that it is information theoretically possible to do this in their toy model, where they modeled black holes as collections of qubits that were evaporating via release of individual qubits, and there was internal dynamics of scrambling. And as a reminder, this is the procedure that they discussed in their paper. So the astute observer who's aware that a message may be thrown into this black hole at some point, they'd like to recover it, collects the radiation from the black hole since its formation in order to acquire a system that's maximally entangled with the black hole. And this is achieved once they wait until the page time, which is the point at which half of the qubits have evaporated. So now, having collected this radiation, the observer waits for the message to be thrown into the black hole. And in Hayden and Preskill's model, the black hole, upon the message being thrown in, it evolves via some deterministic unitary transformation, which thoroughly and quickly mixes this message into the black hole state. So once this has happened, the observer who wants to reconstruct this message continues collecting the Hawking radiation from the black hole. And Hayden and Preskill showed that it is possible to run this through a decoder or recovery channel, which reconstructs the message. And like I said, you can do anything that you could have done with the original message, with the reconstructed message. And for those who prefer a circuit style diagram of this procedure, this is one. So you can see we have the black hole, and it's maximally entangled with its radiation, which was emitted before any message was thrown in. And we have the message here, and the message, if it's not in a pure state, has some purification. And there's some unitary evolution in Hayden-Preskill's model that acts on the black hole and the message. And then the black hole continues to radiate, and there's some part of it left over. And the observer collects the radiation from before and after and runs it through the decoder, producing the recovered message. And an important observation is that any entanglement structure between the message and the purification of the message is retained between the recovered message and the purification of the message. So now, if you look at this procedure, you'll notice that there isn't really much said about what is required for something to be a candidate message. Really, you just need it to be a quantum system, which is smaller than the black hole. And in particular, you'll notice that the black hole itself is modeled as a collection of qubits, a quantum system. So it seems possible that a candidate message is, in fact, a smaller black hole. So this is the question we'd like to consider in our thought experiment. So what if this message is itself a smaller black hole, which would then throw into the larger black hole and attempt to recover the message using the Hayden-Preskill protocol? So now, let me describe our thought experiment. So first, let me introduce player one in the thought experiment. This is our larger black hole who is going to be receiving the message. The message will be thrown into this black hole. And the black hole is formed from the collapse of matter in a pure state. And as per the Hayden-Preskill thought experiment, the original one, it's modeled as a collection of qubits and evaporates via release of individual qubits. And then qubits in the interior undergo scrambling dynamics. And for the purpose of our thought experiment, in order to do the Hayden-Preskill protocol, we assume that the asymptotic observer has been collecting the Hawking radiation from this black hole since it formed. So now let me introduce player number 2. This is our unsuspecting victim, black hole 2, who is going to be thrown into black hole 1. And this black hole is smaller than black hole 1. And we choose it to be much smaller than black hole 1 in order to be able to easily identify the radiation from the two black holes, distinguish it, because that way the temperature is dramatically different enough that we can easily distinguish radiation from the two different black holes. But it's still a macroscopic object. And this black hole is also formed from the collapse of matter in a pure state. And similarly, it's modeled as a collection of qubits, just like the first one. And we also, for the purpose of our thought experiment, will assume that an asymptotic observer has been collecting the Hawking radiation from this black hole since it formed. And you might be concerned that some of the Hawking radiation might fall in, like from 1 might fall into 2, or from 2 might fall into 1, so you couldn't collect all of it. But you can imagine that there's a Dyson sphere around each of them, like two Dyson spheres collecting the radiation separately, or you could imagine that the black holes are in regions that are connected by initially non-traversable wormholes, which become traversable at the appropriate time. So you can get around this problem as long as you engineer the setup appropriately. But now, like I've been alluding to, we'll define a time at which black hole 2 fall into black hole 1. And this is what we engineer in our thought experiment. And we define this to be the time at which the singularity of black hole 2 is fully contained within the horizon of black hole 1. And we'll choose this time to have a couple properties. We'll choose it to be after the point at which the emitted radiation from black hole 1 is maximally entangled with black hole 1, because that was required for the Hayden-Preskill protocol to do the recovery. And then we will also choose this time of consumption to be after the page time of black hole 2. And the reasons for that will become evident in a moment. So now, once black hole 2 has fallen into black hole 1, we will assume that the asymptotic observer continues collecting the Hawking radiation from black hole 1. And now you'll notice that the asymptotic observer has all the ingredients required to perform the Hayden-Preskill recovery. So they've acquired the system maximally entangled with black hole 1 by collecting its radiation since it formed. Then the message has been thrown into black hole 1, which is the black hole 2 falling into black hole 1. And the message here is the state of black hole 2 when it fell into black hole 1. And then the observer continued collecting the released Hawking radiation from black hole 1. So now they just need to run it through their decoder to reconstruct the state of black hole 2. And here is the circuit style diagram for our particular setup. And it's essentially the same, except now the message has been replaced by black hole 2 here, the smaller black hole. And you see that it's maximally entangled with its emitted radiation from before it fell in. And you'll see that the radiation from before and after black hole 2 fell in is being collected by the asymptotic observer, who's going to run that through their decoder to decode the state of black hole 2. And the asymptotic observer is also collecting this radiation from black hole 2 from before it fell into black hole 1. So as you can see, the asymptotic observer in our thought experiment is quite the collector of subsystems. So they've collected a number of subsystems which are of particular interest, which consist of the qubits that are initially associated with black hole 2. So like I said, when I was defining the time of consumption, we chose it to be after the page time of black hole 2. So we can bipartition the radiation from black hole 2 from before it fell in into its early and late radiation, where early and late are defined relative to its page time. And so the observer has collected both of these things because they've collected all of the radiation from black hole 2. And they've also collected this, or reconstructed this state of black hole 2 at the time of consumption via the Hayden-Preskill protocol. And a couple of things to notice about these systems. So like I said, they're all associated with black hole 2, just for clarity, although I use numbers 1, 2, 3. They're all associated with black hole 2. They also together make up a pure system. And they're also all located at asymptotic infinity. So all of them can be encoded into a spin chain, for example. So they're all at asymptotic infinity. And also, most of the qubits are in this subsystem 1, as I've called it. So now I'd like to argue a couple claims. And I'm they're of interest because they seem to be contradictory. So the first claim is that this subsystem 2, which is the late Hawking radiation from black hole 2, is nearly maximally entangled with 1, which is the early Hawking radiation from black hole 2. And I'll argue that by applying Page's theorem, which I'm sure many of you are familiar with, but as a quick reminder, it's the statement that if you have some statistically typical system, which is bipartitioned into A and B subsystems of dimensions m and n, where A is the smaller subsystem, if m and n are large enough, so they're of large enough dimension, then the average entropy will be given by this expression here. And that's important because if you assume that the total system AB is pure, and then assume the system size is as appropriate, then that implies that the smaller subsystem A has this entropy log of the dimensionality, which is implies that it's close to maximally mixed. So now we can apply this theorem to our particular case, where subsystem A will be the qubits of 2 and 3 here, so the late Hawking radiation of black hole 2 and the reconstructed state of black hole 2. And then system B is the early Hawking radiation of black hole 2. And like I said, system B is the one that's larger, and this contains most of the qubits. So, and also, like I said, it's a pure total system, and we can choose the system sizes to be large enough. And so that implies that subsystem made up of qubits from 2 and 3 here is close to maximally mixed. And because there isn't any unitary that's creating any entanglement with this 2 and 3 and anything other than 1, it must be nearly maximally mixed because it's nearly maximally entangled with 1. And so then you can trace out the qubits of subsystem 3, which then implies that 2 is nearly maximally mixed. And so subsystem 2 is nearly maximally entangled with subsystem 1. So that's the first claim that I'd like to argue. The second claim...
Liz, can I ask a question?
Yes.
Just so I understand, these subsystems 1, 2, and 3 together are just the second black hole?
Yes. So this is the radiation.
And I thought number 1 was essentially all of the radiation until the page time?
Yes, that's right.
Why do you say that 2 and 3 are a smaller subsystem compared to 1? Aren't they then equal?
So we defined it to be, going back. It's just delta qubits larger.
Oh, so it's a little bit more than the
Yeah,
page. That's all you meant by that.
Yeah, yeah.
And the second question is, why are you, the way you're presenting this is almost as if it was somehow not, I mean, as if it was maybe controversial, but this is just the standard statements of the Page theorem for a black hole, right?
Yes.
Good.
Okay. Okay, so yeah, sorry. Going back to claim, so claim 2 is the second claim I'd like to argue, which is that 3 is highly entangled with 2, and 3 is the reconstructed state of black hole 2, and 2 is the late radiation from black hole 2. And so Hawking's standard calculation implies that there's a high degree of entanglement across the horizon of black hole 2 just before it falls into black hole 1. And so the qubits identified with black hole 2's interior and those identified with its late radiation should be highly entangled.
I'm sorry, can I ask another question?
Yes.
So you just concluded that 2 and 3 together are basically in a maximally mixed state?
Yes.
How do you define two portions of a non-pure state being highly entangled with each other, especially for a maximally mixed one? What's the definition?
Wait, sorry, could you repeat the question?
I'm trying to understand what definition you're using for highly entangled or nearly maximal. Oh, I'm sorry. Are you claiming that 2 is maximally entangled with 3, or?
So I'm claiming the first claim is that 2 is nearly maximally entangled with 1.
Yeah, that's clear. Okay.
And then the second claim, which I haven't quite finished arguing, is that 3 is highly entangled with 2.
That's the one I want to ask about.
Okay.
What do you mean by that? Because together they're not in a pure state. So what measure of entanglement are you using in this context?
Can I finish the slide first, and then maybe it'll be clearer, and then we can discuss it again.
Well, I'm just asking what that line means. I am kind of reluctant to.
Yes, maybe I can comment on that. So
okay.
The measure of entanglement here, it's It's the standard second half of the firewalls argument where they argue that the black hole interior modes and the late time Hawking radiation should also be maximally entangled. That kind of combined with the first statement make a paradox. So I guess one way of talking about it is to just talk about the mutual information between
but this has nothing to do with, I mean, we don't need to talk about fireballs or black holes for this discussion, right? This is just a system of qubits that you've divided into slightly more than half. That's part one. And then you divided the remaining half into parts 2 and 3. And so they're maximally mixed.
Right, but
I don't understand how 2 and 3 can be entangled with each other by any reasonable entanglement measure.
Yeah, I agree. So what I'm saying is, and Liz will get to this later on in the talk, but the point is that the Page's theorem argument, the one just from entangled systems, shows you that the 2-3 system is maximally entangled with the 1 system. And the argument that 2 and 3 should be highly entangled with each other that really requires GR, because that comes from like Hawking type arguments about like this cartoon picture of pair productions.
But then you're secretly switching to a completely different model, right? Sorry, Jeff?
When you say that the Hayden-Preskill reconstruction is reconstructing the microscopic information in the black hole, it's not reconstructing everything that's in the black hole interior, because the stuff in the black hole interior like has already escaped out into the early radiation.
Yeah, I mean, I don't disagree with any of this, but I think that it might be productive at this point to let Liz give her argument, and then we will explain in what way we agree with the things that you're saying. I think that might make things clear. Like we're not trying to say that that this claim 2 is true. We're trying to say that were this claim 2 true, then there would be a contradiction, and then we're going to argue in what way this claim 2 is reliable. If that is satisfying.
Yeah, maybe I should continue because we're also running a little low on time. So let me argue for this claim 2 based on the assumptions that we made in this this thought experiment. So like I said, I already said this one, but Hawking's calculation implies a high degree of entanglement across the horizon of black hole 2 before it falls into black hole 1. And so we should have a high degree of entanglement. So we should have the qubits that are identified with black hole 2's interior and those identified with the late radiation are highly entangled. Now, crossing the event horizon of black hole 1 shouldn't change the entanglement structure of a quantum system. And we've modeled the black hole 2 as a quantum system, so it shouldn't change the entanglement structure of the state of black hole 2 when it crosses the event horizon of black hole 1. And the recovery protocol in Hayden-Preskill involves only local operations and classical communication. And that's important because those operations don't change the entanglement structure. So the entanglement structure of 3 should be the same, the reconstructed state should be the same as the state of the original state when it crossed into black hole 1. And so that suggests that 3, which is this reconstructed state of black hole 2, should be highly entangled with the late Hawking radiation of black hole 2.
I guess here you are identifying the reconstructed black hole 2 with the original black hole 2 interior, but these two are not the same. Right?
Yeah. Well, we're arguing that it has the same entanglement structure.
But the original interior of black 2 is actually belong to 1, not belong to the original black hole 2 anymore.
Yeah, I mean, I think that both Jenbin and Jeff, both of you are kind of trying to make an argument from the perspective of already knowing the answer. So like you wouldn't have said any of this stuff before EREPR. So like we're just trying to pose a paradox without invoking yet EREPR type thinking. And then we will start to argue why that sort of thinking is necessary to resolve this sharpened version of the paradox. But so I appreciate the question.
Can you clarify that you are saying that this system 1 and system 2 and system 3 is just a kind of few, quote, quote, a few qubits emitted from black hole 1, right? And with the same amount of entropy. Is this whole system you're claiming to be completely pure?
Yes.
So system 3 is a few qubits from the perspective of black hole 1, but it is not a few qubits from the perspective of black hole 2.
So you're saying that these three things are not entangled with the black hole 1 at all?
Yes, after the Hayden-Preskill procedure, that should be true.
After the procedure, right? I mean,
yeah.
And you have to extract. Okay. So
and importantly, the number of extra qubits over the page time that you need in order to reconstruct a message needs to be at least as large as the message itself.
Yeah, sure. But yeah, after reconstruction, you're doing extraction protocol.
Yeah.
Okay.
Okay. So as you probably noticed, these two statements, these two claims that we argued, seem to be in contradiction with each other because, so the first claim is that 2 is nearly maximally entangled with 1, but then 3 is supposed to be highly entangled with 2. So this looks like a violation of monogamy of entanglement, which sounds very reminiscent of the original firewall paradox, which I'm sure many of you are familiar with, but it's the attention between these 4 postulates: unitary evolution of the black hole, validity of semi-classical field theory far from the black hole, and then the fact that the black hole should look like a standard quantum system with discrete energy levels when viewed from far away, with the entropy given by the Bekenstein-Hawking entropy, and then no drama at the horizon. And this original paradox also looks like it gives you a violation of monogamy of entanglement because postulates 1 and 3 imply maximal entanglement between the late and early Hawking radiation. And then 2 and 4 look like they imply that a portion of the late Hawking radiation is highly entangled with the modes in the black hole interior. But what makes this different from the original paradox is that many of the solutions to the original paradox appeal to this special role of the horizon by effectively hiding a portion of the space-time or some other special portion properties of the horizon. And for example, these particular solutions are just a couple examples. But in our case, the systems that are violating monogamy of entanglement are all held by the asymptotic observer, which suggests that this cannot be resolved by appealing to strong gravitational effects or special properties of a horizon. So that seems to make this different or sharpened version of the original paradox. And so then, having presented a problem, natural question is how to resolve this problem.
Sorry, maybe I'm not getting what's the problem, because you are claiming this is after extraction, right? So you're using your bath or whatever early Hawking radiation to decode the information from a few qubits. So you're kind of affecting that system. So it's not like this whole quantum state you have. You can just decode black hole 2 using early Hawking radiation.
Yeah, I think Yasunori, you're like anticipating what we're going to say.
Okay.
But
okay, so
hopefully you will agree that what we're going to say is somewhat similar to what you just said.
Yeah. Okay. So that's why I didn't get the
I don't understand the statement that it's somehow different from AMS and its resolution through things like ER equals EPR. I mean, in the case of a single black hole, you would also say that the radiation is held by a distant observer, and that radiation is the same thing in those approaches as the interior that you find when you jump in. Why wouldn't the interior again be the same thing as the radiation? I don't see what the extra layer of another black hole is doing here.
Well, I guess it's less clear that you can make that claim in that.
I don't think so at all. I think that it's completely straightforward extension of the original proposal. I don't see at which point it would fail. It would be nice to point out where it fails.
Where what fails?
I mean, I'm not convinced that proposal can be built out into a complete theory, but that's a separate issue. I don't, if I accept its various assumptions, I don't understand how it fails in the 2 black hole case if we believe it works for the case of just 1 black hole.
Sorry, when you're saying it fails, do you mean what do you mean fails? The paradox? Yeah, or like, so what I'm talking about this, the
The
very,
resolution of the paradox. I mean, I thought that you were trying to build something
oh,
that cannot be solved by ER equals EPR, even if you believe that ER equals EPR works in the original setting of, let's say, one black hole.
Yeah,
Anyway,
guess,
I think I should let you go on, but I don't yet see how the second layer helps.
okay.
right, let me say one thing and then you can continue. So the one thing that I wanted to say is that one thing that's different here between this thought experiment and the normal AMPS thought experiment is that this thought experiment does not explicitly require the person who is trying to operationally diagnose violation of monogamy of entanglement to ever convert themselves into an infalling observer. So this is an experiment that can in principle be done completely at asymptotic infinity. And then they can see the 3 qubits that are supposed to be violating monogamy and have them in their hands, like at the level presented at this point. Whereas if you wanted to do the AMPS experiment, you would need to do something on the outside and then become an infalling observer and then do something with something on the inside.
But that's because extra paradox you are adding has almost nothing to do with a black hole, right? You just do the Hayden-Preskill reconstruction. You are trying to get entanglement between different systems and the information you wanted to recover, right? That's what you want to reproduce. But then you're using a bath, both maximally entangled with the bath. And how come these 2 different systems and the information you extracted can be because you're using kind of measurement? I mean, that's
I mean, again, Yasunori, if you have the same
sorry, I just
if you have the same question like 5 minutes from now, then you can ask it again. But I think that you'll see that what we're going to say is analogous to what you're saying.
But I'm sorry, but there's only one way to be sure that the qubit that you're seeing is really half of the vacuum at the horizon. And that's by crossing the horizon. You don't get to declare that the thing that you're seeing in your example is somehow the inside of a black hole, but not in the original case with only one black hole. Why don't you say that the thing that purifies some outgoing Hawking particle in the earlier Hawking radiation isn't the inside of a black hole? I mean, I don't understand why you get to say that, or what the second black hole did to make you.
I mean, I think we're just trying to operationalize the thought experiment into something that someone can actually perform as much as possible. So to take the parts where, like for example, famously in Hayden-Harlow, one of the things that they argued is that this distillation of a Bell pair between the early and late time Hawking radiation takes a very long time. And for certain classes of black holes, by the time that you extract that thing, the black hole interior has completely evaporated. And so I'm not saying that that is a complete resolution to the information paradox, but that line of thinking suggests that thinking operationally about how, as a quantum information, even experimentalist, you would try to observe the violation of monogamy is a useful way of thinking about this kind of question. And this is just an attempt to do that by using Hayden-Preskill as part of the procedure.
Ning, I feel like to make an argument that you have a paradox in your case, you need to assume that your Hayden-Preskill thing will eventually pull out the interior thing. I think that requires 2 assumptions. One, it requires assuming, sorry, what? Oh, I'm getting some feedback, but one, it requires assuming that the black hole from the point of view of an outside observer is some quantum system. And 2, it requires assuming that the interior mode that the late time Hawking quantum was entangled with is encoded in that quantum system even after the page time. But if you have those 2 things, then you just with the original firewall argument, you already have with those 2 assumptions, you already have a paradox without talking about someone jumping in, because you can just talk about the black hole from the point of view of an exterior observer. And you can already make an argument that the late time Hawking quanta has to be entangled with that.
I mean, I don't really care as much about making an argument as I do about doing something that I can operationally observe. And I don't think that it's true that in the original AMPS argument, someone that never crosses the horizon can observe a violation of monogamy.
It feels a lot easier than doing a Hayden-Preskill thing.
I mean,
doing the Hayden-Preskill is making it exponentially harder to do anything.
I mean, yeah, but at least I can write down a circuit for it, or a circuit diagram for it. that an asymptotic observer could make. But anyway, I think that we should let Liz continue, and maybe you'll be happier at the end, or maybe you won't. But that's up to you guys.
Okay. So like I was saying, we presented a problem, which is, people have some opinions about whether it's a problem. But if you think it's a problem, then you'd like to ask the next question you'd like to ask is how to resolve this apparent contradiction. And one observation we made is that in the original Hayden-Preskill thought experiment, and then in the way that we originally presented our thought experiment, there's no reference to decoherence in the process. And I'd like to claim that properly accounting for decoherence in this setting will resolve the problem. And let me argue for that as follows. So first, a reminder, decoherence is the observation that quantum systems interacting with some environment will become entangled with or leak information into the environment. And importantly, one result of this is that the density matrix of that quantum system becomes nearly diagonal in some special basis, which is determined by the nature of the interactions. And often this is paired with the Everett view of quantum mechanics. It's a useful perspective. It's a philosophical view, but it's a useful way to conceptualize kind of what's going on. And in this view, the claim is that measurement restricts an observer to a branch of the wave function, which corresponds to a particular measurement outcome. So you have some global wave function, and then upon measurement, the observer is restricted to some branch. And at first glance, it would look like that this arbitrarily chooses out some basis into which the global wave function is decomposed into branches. But that's why this is usually paired with decoherence, because decoherence gives some special basis for the decomposition of the global wave function into branches. So this is a useful perspective to kind of visualize or conceptualize what's happening. And I'd also like to give an example of how decoherence works in this particular setting, because claiming that it's going to resolve our problem. And so you can consider various quantum numbers quantities that have a range of possible values. So for example, the momentum of an emitting Hawking quanta has a range of possible outgoing momenta. And so a branch in this case would then correspond to a definite geometry, which corresponds to a choice of momentum for each emitted Hawking mode. And then because of conservation of momentum, by extension, that gives us a definite position and momentum for the black hole. So that's an example of how what a branch would be in this case. And then at non-asymptotic values of t, the total state consists of some ensemble of such geometries. And then branching in this picture would occur whenever a Hawking quantum interacts with something. So that's the measurement in this particular example. And as the Hawking modes experience these interactions, the black hole decoheres into some preferred basis. So now, like I've been saying, the claim is that properly accounting for decoherence, as I just described, will resolve the contradiction. And so let me argue for it as follows. So describing the process by which black hole 2 falls into black hole 1, this requires specifying a definite point in time at which black hole 2 crosses the event horizon of black hole 1. And this requires a definite geometry, or maybe a subset of geometries. And because of this, that suggests that the process must occur on a branch or a subset of branches instead of on the global wave function. But the asymptotic observer only has access to the global wave function. So that suggests that the global or asymptotic observer cannot actually possess the reconstructed state of black hole 2. And so that suggests that we can resolve the problem by observing that the global observer does not in fact possess the 3 definite subsystems in violation of monogamy of entanglement. So let me quickly summarize, again, because I'm a little short on time, but I'll quickly summarize what I discussed. So first, I described a version of the Hayden-Preskill thought experiment in which the message was itself a smaller black hole. Then argued that the thought experiment resulted in a violation of monogamy of entanglement amongst modes at asymptotic infinity. I compared this case to the original Amps paradox and discussed how it might be different from the original Amps paradox in that all of the subsystems are at asymptotic infinity. then argued that accounting for decoherence will alleviate the problem. Maybe it's not the only solution, but we argued that it alleviates the tension. And a final comment is it might be interesting to think about whether there's a connection between this and the island story, which seems to have maybe some structural similarity in these cases where we have a black hole that's then coupled to some auxiliary system. It sounds similar to having a quantum system with the environment, which is similar to the decoherence story. So maybe there's a relationship there, which would be interesting to think about. So thank you for listening. And I would take more questions, but I don't know if the organizers would like to save those for the discussion section since we went over time.
Maybe we should reserve for the discussion sessions.
Okay. Well,
Thank
thank you for listening.